Alright, howdy y'alls. This is the Diabolic vtutor, and we're here to carry on with the trig functions, basically expanding on the previous stream, just doing mostly problems, and then going over angles that are greater than pi over 3, pi over 6, etc. The other angles that lie on other quadrants other than quadrant 1. So here we are again. Let's just do a little bit of the review. We're going to save the different angles for last. So a little bit of a review from last time. We're going to start with some basic trig functions. Problems, of course. So for example, if we're tasked with doing cosine of 30 degrees, what's that going to be? So in this situation, we have a generic unwritten triangle, right triangle, and all we have to do is apply the cosine function to this one. So we have to summon in our mind's eye the triangle that has the 30 degrees, and that's just going to be the classic 30, 60, 90, which again you should probably commit to memory at some point. So that's going to be here. The 30 degrees is the slim one, and then if you remember the particular ratios, it's going to be 1 to root 3 to 2. And again, we're focusing our eyeball here on the 30 degree and cosine, if you recall from your SOHCAHTOA days. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and the tangent is opposite over adjacent. Do recall that the trig functions, if you input an angle into your trig functions, it's supposed to give you a ratio. This is just going to be standard function type of deal, similar to as a subcategory of f of x. Alright. Again, this is just review from the last stream. We are dealing with the cosine in this particular case. So right here, it's going to be the adjacent relative to the hypotenuse. So from this angle right here that we're staring at, the adjacent one is going to be root 3. And then the hypotenuse is always the longest side. In this situation, it's that one right there. Always going to be opening up. It's the side to which the 90 degree opens up towards, which is going to be 2. So again, that's the cosine ratio. Cosine of this particular angle there will give you the ratio between this adjacent side relative to the hypotenuse, which gets us this one. And then we're done. That's it for the standard problem right there with the invisible triangle. Again, that triangle is in our mind's eye. And then we have another problem. Let's do this one. So we're doing tangent. Oh, that's a weird looking t. So tangent of pi over 3. This is in radians, unfortunately. So if you're not used to radians, then you just manually convert into degrees. So we start off with the pi over 3. We wish to convert from radians into degrees. So therefore, all you need to have is some sort of conversion rate. So here's going to be our conversion rate. It's going to be 180 degrees relative to, for every pi. Right there. So memorize that. Either way, you have to memorize something at some point. So just as a reminder, that one comes from full circle. So if you go full circle, here's the center of the circle. If you go full circle, that's going to be 360 degrees. And of course, for the radian measure, full circle for radians is going to be 2 pi. So full circle is 360 degrees and full circle is 2 pi. So if you simplify this one, since they're equal, you will get 180 over pi. Hence our conversion rate right over there. So delete that. We don't need that anymore. So let's just run through the conversion rate. This is technically over 1. So we just multiply straight across, but please simplify before you multiply. So since we have a pi on top and we have a pi on the bottom, we can just cancel those out. And then we're left with a 1 over 3. That's the 3, that's the 1, so it's 1 over 3. Let me just rewrite that. So we have 1/3 times 180, that's just going to be 60 degrees. So thus our problem, again, if you like it in degrees, is going to be tangent. What is tangent of 60 degrees? We're not given a triangle, and this is also a nice angle. You need to learn to start recognizing these very favorable angles. But 60 degrees, it harks to our 30, 60, 90 yet again. So here it is in our mind's eye, which hopefully we're going to memorize that. So 60 degrees is the larger of the two. That's 60. This is going to be the 30. Don't forget the ratios. This one opens up to the medium side, which is root 3. And then the 30 opens up to the small side, which is the 1. The hypotenuse is always going to be 2. For the ratios. Not for the actual triangle, but since we're working with an imaginary reference triangle, then we can go with the smallest ratios. So tangent of 60 degrees, what are we doing? We're looking from this particular angle. Tangent, that's going to be opposite, the ratio of the opposite relative to the adjacent. So from this angle, that's the opposite. And then this is the adjacent. So we have root 3 over 1. So that simplifies into root 3. And then we're done with this particular situation. That's it. So a bit of memorization. Unfortunately, that just comes with the territory. If you don't do the memorization problems, you're basically doing calculator problems because nobody expects you to memorize any of these ratios. Aside from the special right triangles and the something called interquadrant angles, which we're not going to cover, at least not in this stream. Alright, let's do an actual drawing problem where we're actually given a particular triangle. Start with the easy one, of course. So here's a triangle. It's going to be a right triangle because that's pretty much the situations we will only deal with for now. Only right triangles. We're going to call this one angle alpha. We're going to call this one theta. And here is a 4. Here is a 10. First question is going to ask us, what's tangent of alpha? Second question, what is tangent of theta? Third question, what is sine of alpha? Let me just move that just a little bit. Right over there. So going from top to bottom, starting with this tangent of alpha right there, we're looking at this particular angle. What's tangent? Tangent is simply the ratio of opposite relative to adjacent. So, looking there. Draw the old eyeball. So from this particular perspective, it's going to be opposite over adjacent. So 4/10, that simplifies into 2/5. Divide top and bottom by 2. That's the answer for that one. Not too bad. And the next problem up, we're now dealing with tangent of theta. So we're no longer focusing on this particular angle. No longer this perspective, so let's shift our perspective to right over there. So from this new perspective, we now have a different opposite. We're still dealing with tangents, so tangent relative to this particular angle, so the opposite over adjacent. So from this new perspective, what is going to be the opposite? It's going to be 10. What's going to be adjacent from this new perspective? It's just the 4. So as you see, it's the flipped version of what we had before. Instead of 4/10, we have 10/4. Simplifies into 5 over 2. And then that's it. And then third question for this set, we have sine of alpha. So we need to move back over to this perspective. So from that perspective, we're trying to do the sine function to this angle. What's sine again? Right over there. So sine should give us the ratio of opposite over hypotenuse. So from this perspective, that's the opposite. We're not given the hypotenuse, unfortunately, so we have to resort to Pythagorean identity to solve for the hypotenuse. And that's just going to be a squared plus b squared equals c squared. And since we have h here as a letter already, we're not going to call it c squared, we'll just call it h squared. Alright. So which of these is a and which of those is b? It doesn't really matter, quite frankly. So I'm going to arbitrarily set this one to a, arbitrarily set this one to b. Just stay consistent. So 10 squared plus 4 squared is equal to h squared. So we're going to have 100 plus 16. We'll take the square. Oh, let's not do that yet. So therefore, rearranging h squared is equal to 116. Take the square root of both sides. H is equal to, we're going to drop the negative value and keeping only the positive. So positive 116. Is it simplifiable? I don't remember. Oh, yes, it is. So 116 is going to be 4 times what? 29? Yeah. So there it is. We can therefore simplify this just a little bit. So it becomes 2 root 29. There we go. So we can replace this h. 2 times root 29. And then now we can finally apply the sine function to the alpha angle. Again, that's sine. It's going to be the ratio of opposite over hypotenuse. So opposite, from our perspective, opposite over hypotenuse. So 4 over 2 root 29. There's a little bit of simplification to perform for this one. First we need to rationalize, and then we need to simplify top and bottom by 2. Let's do the top and bottom divide by 2 first. So divide by 2, and then divide by 2. And to rationalize, we'll just follow a very basic algorithm. Top and bottom times square root of 29. Final cleanup step. This one, the square roots undo each other, kind of. And we get 29 on bottom, and then we copy paste 2 times 29. And that's it for sine of theta. So again, sine of theta, I said theta, I'm sorry, sine alpha is equal to this thing right here. And then we're done with these basic problems. So again, not too bad, just get used to the situations. Alright, so move on to slightly more complicated problems. Here's the first up. And this thing right here. Sometimes drawing these is kind of a pain. Alright, there we go. So the given side here is 2, and then we have an angle theta right there. And we're also given tangent of theta is equal to 3. And the question asks, if this is h, then h is equal to what? So that is the particular problem. So a few things to make note of. This is actually a triangle that's drawn for us, so therefore it has definite values right there. So not just ratios. So the thing about tangents, cosines, or any trig function rather, the thing with any trig function is that trig functions only give you reduced ratios. So what that means is, if I walked by a classroom, for example, and I peeked into the classroom and I told you that the ratio of tables to chairs is 1 to 2, let me write that down. So again, I walked by a classroom, I peeked into the classroom just to get a glimpse of and counted the number of tables and chairs, and then I gave you a ratio, and I told you that the ratio of tables to chairs is 1 to 2. What does this actually mean? It doesn't mean that there's only one table and only 2 chairs. It just means that this is the numeric relationship proportion between those two quantities. So there could very well be 10 tables and 20 chairs. There could very well be 40 tables and 80 chairs. You don't know. You only have the reduced ratio. So there's no clue. I'd have to give you one of these values in order for you to figure out how many tables there actually are. So for example, if I told you that there are actually 7 tables, given this particular ratio of tables to chairs, so again, I'm telling you that the ratio of tables to chairs in a particular room is 1 to 2, and if I tell you that there are 7 tables, then you can set up a proportions. So if the proportion is 1 to 2 for tables and chairs, and you actually have 7 tables, then therefore we should have C amount of chairs. And then you do the cross multiplication. C is therefore equal to 14, and there you go. And that should give you the total number of chairs. So I'm mentioning this analogy strictly because trig functions give us ratios. So in this problem, tangent of theta, which is right there, is just a 3. This is just one number, right? But don't forget, you are always entitled to take a number and put it over 1 if you wish to generate some sort of fraction to work with for your mechanics. So 3, you can rewrite it as 3 over 1. So therefore, that's the ratio between opposite to adjacent. But don't forget, this is just a ratio. So if you look here, that's where we're focusing on. Let's draw the eyeball right there. Funky looking eyeball right there. So from that particular perspective, the ratio of this opposite side to this adjacent side is 3 to 1. This is just a ratio. But since we have a definite value of 2, then there's a definite value here as well. So don't put 3 right there, because that's not true. Why not? So if you took the ratio with these actual values, you see if you take tangent of this angle with what we've written here, it would be opposite 3 over adjacent 2. 3/2 is not what's given in the problem. The ratio is 3 to 1, not 3 to 2. So don't just copy paste this number right there. So what we can do instead is we can just, for now, just put a variable, anything you wish. Just put generic x. Alright, so starting over again, we're given this inner problem. We can convert this 3 into a ratio, 3 to 1. That's the ratio of this x opposite to this 2 adjacent. So we can equate those as a proportion. So opposite is, the actual opposite is x relative to the actual adjacent is 2. So that's the definite values. These are the definite values, and this is just the ratio that is given as true from the statement. Alright, so that's what we're doing. All you need to do is cross multiply. X is therefore equal to 6. So now we know this number here is not, we now know what x is. It's just going to be 6. I'm not going to put 6 is equal to x. I'm going to put x is equal to 6. I guess it's a little bit of pedantic. Alright, put it right there. There we go. And of course, once we have 2 definite sides of a right triangle, we can use Pythagorean identity to figure out the last one, which is what the question is asking for. So let us do that. A squared, arbitrarily, b squared equals c squared. Always the longest side. It's always the loner one right here. Since we have h, let's keep it as a letter h. Okay. So instead of writing the squared here, I'm just going to write square root of both sides. So to clear this, you can just take the square root of this side and that side. Alright, whoops. So let's simplify that nonsense. So 2 squared is 4, and then, did I say 6? 2 squared is 4, no, I said that. correctly. So 2 squared is 4, and then the 6 squared is 36. And thus that simplifies into square root of 40. So h is equal to the square root of 40. But this is simplifiable. You should simplify it if you can. That just consists of 4 times 10 in the radical. We can take the square root of the 4. So it becomes 2 root 10. And that'll be the final answer. Delete that. 2 root 10. And then we're done with this particular problem. So the main thing that I want to point out for this problem is, of course, the tangent functions. If you apply the tangent function, or rather, if you apply any trig function to a particular angle, it gives you a reduced ratio fraction. So that's a reduced ratio. Not the actual numbers. It doesn't mean that the opposite length is actually 3 and the adjacent is just a 1. It's just that the 3 to 1 is a reduced ratio. If you're given discrete values, set up the proportions. And that'll get you the true side length, like 6 and 2 root 10. And thankfully I've pre-written these problems. Alright, and the next problem up, it's going to be another similar situation to the one we've just done. Again, I wish to emphasize that the trig functions give you reduced fractions for the ratios. So that's angle alpha. This is 90 degrees. This is side length y, and this is side length 10. And then for this particular problem, we are told that sine of alpha gives us the proportion of 5, 6. And our job is to figure out what's the value of y. Alright, so again, this is a very similar situation. What are we focused on? We are focused on angle alpha, so this particular angle right there. So we're focused there. Let me draw the eyeball. Alright, so from that particular perspective, the ratio, what does the sine function give us as a ratio? It gives us the ratio of opposite relative to hypotenuse. So right away you can see that the ratio value 5 is not equal to the discrete value 10. Not the actual value of 10, so thus we have to set up a proportion. So this is h. We don't know what it is, but all we know is that the ratio of opposite relative to hypotenuse is 5, 6. So set up the proportions. So opposite is 10 relative to hypotenuse, which is h. We don't know what it is at the moment. That's very nice. This is fairly straightforward. 5 times 2 is 10, so therefore 6 times 2 has to give us h. So h is therefore 12. So now we know that's 12. And the question asks, what's the value of y? Well, we have 2 sides given out of 3 for a right triangle, so therefore you can use Pythagorean identity to figure out the last value, y. So a squared plus b squared equals c squared. So a squared plus b squared equals c squared. And feel free to skip your work. Honestly, I'm just showing all the details as much as possible. This is going to be 10. This is going to be 144. And y squared, copy paste. So minus 100 from both sides. We're going to apply square root to both sides, dropping the negative value. So y is therefore equal to positive square root of 44. We can factor out the 4 from the 44, thereby getting 4 times 11. We can take the square root of 4. So final answer, y is equal to 2 root 11. Is that what it's asking for? Yes, it is. Okay, so we are done. The y value is right there. So just to reiterate one more time for this problem, this is what we're given in the problem. It's a reduced fraction ratio. The actual value we're given is 10. So we know that there's a discrepancy because this is supposed to be the ratio between opposite relative to hypotenuse. So because this number is distinct from this one, we know this is a reduced ratio. So therefore, all you need to do is set up the proportion, and then they'll let you figure out one of the unknown sides. And once you have two known sides of a right triangle, just use the good old Pythagorean identity and figure out the last one. Moving on. What do we have? Okay, we have this one. We're going to do the, what is it? Let's do this one. So here's the old right triangle. Here's alpha yet again. We're given the hypotenuse is 3 root 10. This is right angle. Of course, I have to give this. All triangles we're working with will be right triangles, at least for now. And then what else is there supposed to be? Letters. Oh, here it is. So the given information is tangent. Tangent of alpha is equal to 1/3. And then our job is to figure out the area of this particular triangle. So let's say this is triangle A, B, and C. So the area of triangle ABC is equal to what? So kind of a compound problem. We're mixing up the formula for a triangle with this particular situation. So our job is to figure out base and height, and then use the classic formula 1/2 is equal to base times height. But we're only given one particular side, and then we're given a ratio. So what exactly do we do here? All right, let me first, let's move things real quick. So this is our main task. Put it right there. We're given a ratio, but tangent of, what is tangent of alpha? We're looking at this particular angle. And the tangent is going to relate this side opposite here relative to adjacent there. We don't know what those are, so I'm going to use letters for this one. Let's call this one y. Now let's call this one x. So that's it. So tangent of alpha is equal to 1/3. That's pretty bad, right? So unfortunately, there's not too much to work with. So I'm actually go back a step. Let us not use too many different letters. So while it's not wrong to set this one equal to y and set this one equal to x, that's too many letters to talk about. Because there's something nice that we can do instead. So let's not pick y and x. And here's the reason. It gives us the ratio of opposite relative to adjacent. So if we define this one as x, then whatever this is, it should be 3 times what this one is, because that's what the ratio means. I hope that makes sense. Alright, so let me rewrite this. So to be very emphatic here, 1/3 is the ratio of opposite to adjacent. These are not the actual sides, so don't just call this 1 and 3. What we do instead is there's an actual value x. We don't know what that value is, but we know that the bottom number is 3 times that of x. So 3 times x. So x here represents the true length here, and then 3x represents the true length there. So as you see, we define B, C, and AC by using only one letter. So if we use y here and just x there, that's too many unknowns. There are too many unknowns, and then we won't be able to solve for anything. So set up your unknowns very carefully. Alright, so just to make sure this makes sense, the actual length of BC is x, and the actual length of AC is 3 times of that. So if you take this one and you reduce it, since x is not 0, if you divide top by x, you get 1. If you divide bottom by x, you get 3. Isn't that the original ratio we were given? 1/3 right there. Okay. So not to sound like a broken record, but that's the actual ratio of the sides. This is just a reduced ratio. Alright. So what do we do in this particular situation? Well, it's kind of complicated, right? We start off with a ratio. The only thing anchoring this problem with actual values is the hypotenuse, 3√10. So normally I've been harking on about how if you're given two sides of a right triangle, you can use Pythagorean identity to figure out the last side. Well, we're only given one side, and we're given two unknowns, right? But here's the thing, Pythagorean identity is one equation. If you plug this in as a squared, and this one you plug it into b squared, you technically only have x as a variable. So let's just see what happens, okay? So again, the formula is a squared plus b squared equals c squared. If you have a right triangle, which we do, if you plug in this one arbitrarily here, and this one there, we're going to get 3x squared plus b squared, which is x squared. And that should be equal to c squared. So look what happens in this situation. So if you resolve this and then you resolve this, you will only get x terms, which means we can solve for x since it's a single equation with a single unknown. So let's proceed down this route. Simplifying that, for a distributive property of exponent, we're going to get 9x squared. That one is simply x squared. And then this one, distributive property of exponent, 2 to the 3 gives us 9, and then 2 to the radical clears the radical. We get just 10. Alright. So a few things to simplify. This one, since we have 9x squares here and we're adding 1x squared, we have a total of 10 of these x squareds. That's just a 90. So divide both sides by 10, divide by 10, divide by 10. And x squared is therefore equal to 9. If we solve for x, take the square root of left-hand side and right-hand side, drop the negative value, x is equal to positive 3. There it is. So we've used Pythagorean identity on these particular values. Because it's a single unknown, single equation, we solved for x. X is therefore equal to 3. So now we can call this one just 3. And this is 3 times x, which is 3 times 3. So that's going to be 9. So we have all the things required in order to figure out the area of the triangle. Recall that the area of a triangle is going to be 1/2 base times height. From our good old geometry days, yes? It doesn't matter which one you set to the base or the height, as long as you stay consistent. So if we call this one the base, then this will be the height. Always joined by this perpendicular, always joined by 90 degrees. But if you call this the base, then this is just going to be the height. This one is not 90 degrees relative to either this one nor this one. So we just are working with 9s and the 3s. So arbitrarily plug it here, arbitrarily plug it there, which simplifies into 1/2 times base 9, height 3. We're going to get a 27/2. That's going to be the area. Well, we don't know the unit, so I'm going to just put unit squared. That's a good habit. Alright. And that's the answer for this particular problem. Just to recap, you can skip this if you're watching the VOD, obviously. But just to recap, we started off with just this particular ratio and this particular concrete value of 3/10. From this ratio of 1/3, we figured out that, well, if we call this one x, then we can define this side as 3 times that of x, because this is just a reduced ratio. X, as we define it, is the actual side length So therefore, you set the ratio, since the actual length is x, then the other side is going to be 3 times that, because that's a ratio of 1 to 3. Once we've defined the sides in terms of one variable, one unknown, we can set up one more equation, which is just going to be Pythagorean identity. And simplifying that, after substitution, we will get one equation and one unknown, which means we can solve for the single unknown, which is what we did up to this point. And then once we figured out what the small value x is, we can figure out the length of this one, because they're proportions. Now that once we have the 3 and the 9, the actual length of the sides, we can slam dunk those into the area formula, 1/2 base times height, crunch the numbers and get the answer, and then we're good to go. Okay, moving along very swimmingly. We have, oh, this is kind of a, looks like kind of a pain to write, honestly. So here it is. This line here is parallel to this line there. And then between those we have this rectangle thingy. Just to emphasize this one, these two directional arrow means this one's parallel to this one. And then this is going to be 90 degrees here, and then the 90 degrees there. We have this diagonal over there. And what else we're given? If we call this point A, this one's going to be point B, point C, point D. And the given information. Oh, let me move this real quick. Move it right there. Alright. So we're given the perimeter of the figure. Which figure? Figure A, B, C, D. That's going to be equal to 32 units. Furthermore, we have additional givens. We have tangent. We're given tangent of theta. I keep looking in the wrong direction. So tangent of theta is equal to 5/3. Where is theta? Theta should be right here. That's only from here to here. So not this whole thing. Just from here to here. Just the indicated shaded angle. And then we're given one more piece of thing. What is cosine of theta? Alright. Well, I think this problem is overwritten. Let me change something real quick. Let's just do something simple instead. Let's determine the length of dB. Yes. So originally, if I'd kept the problem like this one, right? This answer is actually very easy. I'll explain that why afterwards. So let me just write this. I should keep this right here. I'm going to take this one right here and I'm going to set it aside. This will actually be a very easy problem if this is just a question. And all this extra information is superfluous. So I'm going to take this one and set it aside. And I hope that we'll remember to cover this one. Okay, but the true question that I'm going to do, I'm going to change the question. I'm just going to ask for the length of dB. Alright. Okay, so let's take a step back. What exactly are we doing? We are working with a parallelogram. Recall from your geometry days, we have this nastiness right here. This line is parallel to this line, so we have a bunch of alternate interior congruency. We're told that this is 90 and this is 90. That's fun. So let's start, I guess, pinpointing a few things, right? I'm gonna use a different color just to show the inferences. So all this color as is will be the givens, and this color is an inference. So because this is 90 degrees, then this whole thing, and this whole thing is 180, then therefore this is also 90. And verifying that this is 90 degrees makes this easier to work with. We're given tangent of theta, which is right here. Tangent is going to be opposite relative to adjacent. Let's put some color. So if, call this one light blue, right? That's going to be this particular number up there. That's a reduced number, remember? And then the other one is right here. Yeah. So relative to this theta, this one, this bluish color is going to be opposite, and this red one is going to be adjacent. It doesn't mean, again, that this is 3 and that's 5. No, that's just the reduced ratio. So we can call this one 5x and this will be 3x. That's what we're going to do, yes. Because again, according to this statement right here, the 5 to 3 is just the reduced ratio. This 5x means the actual length from here to there, and this 3x means the actual length from there to there. So if you set up the actual proportions, these are the proportions, and then this is the actual ratio. The actual ratio is 5x to 3x. You can see that the x's will cancel because they're not 0, and will get you back to this reduced fraction. So that's what we know. In addition to that, we are given this other factoid. The perimeter of ABCD is 32 units. Alright. Geometry review, right? Since this is 90 degrees, well, right here, I misspoke. This is 90 degrees. We already figured out that this part right here is 90 degrees. Since this one is 90, then this whole thing, and this whole thing is 180, this one is also 90 by supplementarity. Straight angles are, the sum of angles that make up a straight angle are supplementary. Alright, so since this is 90, and then this is 90, do we know anything else in this situation? What else do we know? Okay, well, we know that, I'm running off colors here, we can figure out that this angle here is congruent to this angle there. So they're called alternate interiors. And what else? Actually, we don't need that. I'm sorry. We don't need that. Here's the other thing. Since this line is parallel to that line, and this is a transversal, since this is 90 right there, then by alternate interior, this is also 90 right here. And since that's 90, then this one right overall is 90, and then this one overall is 90 from the same reason on this particular transversal. So what I'm trying to point out here is this whole thing is just a rectangle. Then we have 90, 90, 90, and this one has to be 90 as well. So this whole shape is a rectangle. And all that is just to verify, if you already saw it, then that's just to verify that this thing is also going to be 5x. And of course, since this is a rectangle, since this is 90, since this is red right here, then this was also red, which is also 3x. And the reason why we're going with this rectangle situation is because we're dealing with a perimeter of a shape. If you're dealing with a perimeter and then the shape is a rectangle, then it's very easy. All you need to do is equate one opposite sides are congruent. And since everything is defined by x, we can therefore generate one equation with one unknown, which is why we're doing this in the first place. So using the perimeter, 32. That's going to be the sum of this, plus this, plus this, plus this. I'm going to drop the color at this point. So let me just put 3x plus 5x plus 3x plus 5x. That's the perimeter. And of course, this is going to be 8 plus 8, which is 16. So 16x is equal to 32. And since, again, this is a one equation, one unknown, we can therefore solve for the unknown. X is therefore equal to 2. And that's absolutely wonderful, because now we can go back and start slam dunking those values of 2 into this one. So this is going to be 2 times 5, which is 10. And this is going to be 2 times 3, which is going to be 6. What's our main objective? Is to figure out the length of dB. So from here to there. And since we have two unknowns of a right triangle, we can simply do a squared plus b squared equals c squared. So let's shortcut this just a little bit. A squared plus b squared equals c squared. Just take the square root of both sides. C is therefore equal to the square root of 136. Is that a nice number? I think it is. It's going to be 4 times 34. We can't take the square root of the 4. That seems to be a recurring theme. So we get 2 root 34. From the good old Pythagorean identity. So therefore we can answer the question. It's going to be 2 root 34. There it is. I should have saved this problem for later. I feel like this is more difficult than some of the other ones, but I guess that's fine. You know what? Before I lose track, let's talk about this one real quick. So this right here was the original question. We can actually answer it right now since everything's already filled out. So if we're taking cosine of theta, that's right here. Cosine is just going to be the ratio of adjacent 6 over hypotenuse 2 root 34. So that one. 6 over 2 root 34. So you can see that's simplifiable. Top and bottom divide by 2. We're going to get 3 over root 34. I'm not going to rationalize this one because I just want to show a point. Did we need to do all this fanciness to get this ratio? And the answer is no. Because this one, you could actually generate the ratio given just these two values, even though they're not the actual lengths of the triangle sides. They're just a reduced ratio. Okay? So here's how we can think about this. This clue right here, tangent of theta is equal to 5 over 3. If you draw an imaginary triangle, if we call this one theta right here, right? Theta, tangent of this theta gives you the ratio of opposite to adjacent. So if you pretend this is 5, then this would be 3. And you notice the word I said pretend, because those aren't the actual lengths. But that's okay though. I just want you to do a squared plus b squared to get c squared right here. So that's going to be 25. That's going to be 9. That gives us 34. Take the square root of 34. So this is going to give us the ratio 34. So these numbers are not the actual length of the sides of the triangle. Those are just the reduced numbers we got from these reduced numbers. But here's the thing though. Since we are applying a cosine function to this triangle, it doesn't matter if these numbers are reduced or not, because in the end you're going to get reduced numbers. Hopefully that makes sense. But let's apply the cosine function to this particular theta. It's going to be adjacent 3 over hypotenuse root 34. And as you notice, that's the exact same thing as what we got before, without having to do all this extra work. So what I'm trying to say is basically when you're going from trig function to trig function, you don't need the actual lengths, because trig functions will give you reduced values. So therefore, we don't need to use this 5/3 to figure out the actual lengths, because we can get the proportions of all three sides thanks to Pythagorean identity. And since we don't care about the actual lengths, then you can set the ratio in the final what the trig is asking for. I felt like that explanation wasn't super clear, but nobody's here. Alright, I guess I should summarize this one real quick. It's kind of a mess though. Let me just redraw it and then summarize real quick, and then we'll move on to the next problem. Again, I wish I had saved this problem for last. So let me just redraw the thing. VOD watchers could definitely skip this again, unless you prefer to have a recap. Alright. Parallel to this one. And then we have here is A. That's a B. This is a C, and this is a D. This one is the old theta. This one is 90 given as 90. This one is given as 90. And two more pieces of information. We're given the perimeter. Shrink this just a bit. Okay. So we're given the perimeter of figure ABCD. And we're given, what was it? Tangent of theta. That's equal to 5/3. And then the modified question asks for the length of dB. Okay, so again, the situation is this. One of the important things to make note of is this figure right here is going to be a rectangle, because once you know it's a rectangle, that simplifies the situation a lot. And I'm not trying to make a very, very exceedingly difficult problem. So typically there's some nice things you can do. Okay. So again, the first information we're given is the perimeter of ABCD. So this one plus this one plus this one plus that one gives us 32. We don't know any of those four sides, so it would be disastrous if you just call the side X, Y, Z, and I ran out of letters, right, didn't I? W. So if we called each of those sides a different letter, then we're going to have X plus Y plus Z plus W is equal to 32. There's way too many unknowns. X, Y, Z, and W. That'll be 4 unknowns, and this is only one equation. So that would be the losing setup. So let us not let us not write too many unknowns. So we suspect that this might be a rectangle. It's not always safe to assume, but this is a problem that's introduced in a trig context, so it's probably not super complicated. So you can probably cheese it by assuming that this side, if you call this one X, then this one is also going to be X. But let's talk about that for a moment. So it's for future problems, don't auto-assume. So this one we're just going to have to justify that if we call this side X, then this other side will also be X. So how do we justify that? Well, this is harking upon the properties that were covered in geometry days. So the job was to show that this is going to be a rectangle, so we can simplify things a lot. Since this is 90 degrees, this is going to be 90. Since this is 90, then this is going to be 90. And of course, since this is a transversal, then alternate interiors are congruent, so therefore this is also 90. Therefore, this is also 90. And by that same token, because this is a transversal crossing these two parallel lines, then since this is 90, then alternate here, this one here is also 90. So we have 4 90 degrees. That's enough to qualify this shape here as a rectangle. So therefore, if we set this part as x, then this one is also going to be x. If we set this one as y, then this one is also y. But that's also a losing setup because we're given one more piece of information, tangent, which relates this one to this one. So we don't need to set x and y's as unknowns. So here's what we can do. Since tangent gives us the ratio of opposite over adjacent from the perspective of theta, from this perspective, the ratio of this one to that one is 5 to 3. But again, that is a reduced ratio. The actual length here is x. So, oh, I said it as x. Just to make things a little easier, we're going to call it 3x. And here's the reason why. If you just call that 3x, then you can easily set the top equal to 5x. We don't have to do it like that. If you really, really, really want to, you can keep this, you can call this as x. It's just that this top number here is going to be kind of annoying. It's going to be a fraction value. You're going to have to call it 5/3 x in order for this ratio to hold true. Because if you do 5/3 of x divided by x, those two will cancel, leaving you with a 5/3, which is equal to 5/3. But I don't know about you, but I don't like setting up fractions like that. So rather than setting it like this, by calling this 1x, we can make things a little easier, in my opinion, by calling this 3x. That's the adjacent. That's the actual length of the adjacent side right here relative to this theta. The actual length is 3x. So if the actual length is 3x, then this one here, the actual length will be 5x. Because again, tangent of theta should give us 5 to 3. Alright. So I feel like this explanation was a lot clearer than before. I hope. And once you have set up those sides in terms of x only, we can summate all 4 sides in order to set it equal, in order to equate it to the given perimeter. So opposite sides of a rectangle are congruent. So if this is 5x, then this is 5x. If that is 3x, then that is 3x. And all you need to do is summate those and equate to 32, which allows us to solve for x. In that case, it was 2. Wait, was it 2? 12 plus 20 is 30. Yeah, it was actually 2. And then once we figure out what the x is, then we can plug that back into there and plug it back into there and use Pythagorean identity to solve for the final thing, which is going to be this length dB, the actual length dB. Yeah. Okay, that's it for that problem. It was kind of a review of old stuff. Hopefully that's useful. Moving on to another problem. I think this paper here is exhausted. Oh, no, there's one more. There's one more. So on this particular sheet of pre-written problems, let's do this final problem. All right. That looks kind of non-proportional. Let me try a little better. Well, we're just going to have to live with this, unfortunately. But here's the given information. We are told that this one is 4 root 5. That's the length from here to there. And this one is also 4 root 5. And again, it's not exactly two-scale drawing, but you'll have to trust the numbers. Okay. So that's 4 root 5. That's 4 root 5. And in addition to that, this is 90. 90. That's also 90. In addition to that, this one is 90, and then this one's 90. And some lettering. Wait, do we need lettering here? No, we don't. Okay, and the entire length of this one from here to there is going to be 12. And we're given this one is defined, this angle here is defined as alpha. So only this angle. So not the entire thing, not that one. So just this particular angle right here is alpha. And our job is to figure out the tangent of alpha. Now let me take that and move it aside. Alright, so a few hidden pieces of information right there. We have 90 here, 90 and 90. Since this is a four-sided figure, we can therefore say that that's going to be also 90 degrees. Let me use a different color. So again, because this is sum of interiors of a four-angle figure polygon, this is 90, this is 90, this is 90. They all need this one plus those other three 90s needs to be 360 degrees. So therefore, this one must be 90 as well. All right. So this is at least a rectangle, but because this side here is equal, like literally you could see the value 4/5 is equal to 4/5, then this one is congruent to this one. And opposite sides of a rectangle are congruent. So if this is 4√5, then this is also 4√5. So if this is 4√5, then this is also 4√5. So this is the one we don't care about too much. We care more about this one because it's related to the triangle we're actually focusing on. We might need this one. I don't think so though. Maybe, maybe not. Alright, so now that we know what this one is right here, let's see, let's take a step back. So we know the length of this side right here. And the actual length is, again, 4√5. So do we have enough to answer the question here? Well, first, what's tangent of this alpha? Tangent is going to be opposite relative to adjacent. And we have neither of those, unfortunately. So we don't know what this is. So temporarily call this one x, and then we don't know what the other one is. Temporarily call that a y. Temporarily. So we know neither of those two, unfortunately. Okay, well, what does that mean for us? So not only are we given a ratio, we're only given one side. So we can't use Pythagorean identity. So we consult the rest of the drawing. Well, what's this 12 here doing, right? Why are we given this particular 12? This 12 here covers the triangle part that we care about. But it also covers this part right there, which isn't directly what we care about. But here's the thing, though. This one right here, what is that? And again, this is just going to be a review of good old geometry days, or maybe good old battle days. We have no idea, right? Alright, so the thing is, this drawing is unfortunately not drawn to scale, so there are a few things you have to point out for yourself. And let me think about the easiest way to go about talking about this. This whole thing is going to be 180 degrees. Since this is 90, then this red angle, I'm going to denote here. Let's just call this beta for now. So if we call this one, this red angle beta, then beta plus alpha should give us 90. Because again, this whole thing should be 180 degrees. You know what? In fact, let me write that out. So straight angle, this is a straight angle, is 180 degrees. That's going to be the sum of these three angles: red angle, beta angle plus 90 degrees plus the alpha. Coming back from the old geometry days. Alright. So we know that. We can subtract the 90 from both sides, so minus 90 degrees, minus 90 degrees. So 90 degrees is simply the sum of beta plus alpha. So what that means is these two sum up to be 90. And here's the goofy thing. Since this is a triangle, this angle here plus that one should also equal 90 because of sum of interiors. So if you want to point out this micro situation, this other situation, so if this angle here, we don't know what it is at the moment, this one plus this one plus that one, let's call this one gamma, right? So alpha plus 90 plus gamma should be equal to 180, sum of interiors, right? For this particular triangle, we moved on from this straight angle. We can subtract 90 from both sides. Therefore, we are going to get alpha plus gamma is equal to 90 degrees. But here's the goofiness. This thing, put it next to there, right? And I hope you see it. Given this and given that, can't we equate those two together? Since this is 90 and this is 90, then by transitive property or substitution, alpha plus gamma is equal to beta plus alpha. If you subtract alpha from both sides, since they are equal measurements, those are one and the same. Which means we don't have to call this one gamma, we can call this one beta. And all that nonsense, what was that for? Well, since that is beta, then this one should be alpha. Because again, this angle, before we denoted it as alpha, since this one plus this one should be equal to 90 degrees, sum of interiors, then we can say this one is also alpha. Alright. So, I hope that dredged up some memories of geometry stuff. And here's the thing though, since these two angles are congruent, and then those two angles are congruent, then triangle number 1 is at least similar to triangle number 2. But one more thing, since they share the exact same hypotenuse, then therefore triangle number 1 is in fact congruent to triangle number 2. If you want to cite that, that's referred to as the HL congruency for right triangles, aka it's the ass proof, the forbidden proof, the forbidden ASS proof. But because this is 90 degrees, then this proof works. If you don't remember, trust me, but you should always practice a little bit of healthy skepticism, right? You can verify that yourself. Alright, so I don't want to bog this problem down too much with all this callback to geometry days. So long story short, what have we done so far? Long story short, again, we figured out that this whole thing is a square using sum of interiors, and then we started equating opposite sides. So 4 root 5, this is 4 root 5, this is also 4 root 5, and then figuring out straight angle and then sum of interiors. If this one is beta, if we call this one beta, then this one's also beta. If this one is also beta and this is alpha, then this one is also alpha. But since these two hypotenuses are the same, then triangle number 1 is congruent to triangle number 2. Wonderful. So now we know that this triangle is in fact the same, is congruent to this triangle, which means we can start redefining our letters to make things much simpler. Alright. Well, here's the fun part, right? Do we want X or do we want Y? Since we know that this is going to be blue X, then because triangle number 1 is congruent to triangle number 2, this one opens up to the blue, then this one opens up to blue, so this one must also be X. Because again, CPCTC, corresponding parts of congruent triangles are congruent. Alright, so now we know that this is X. And here's the thing, again, you might some people might be tempted to set this up as x and set this as y to get the situation, but since we have a 12 here, I'm not going to call that one y. Because if we call that one y, we have two unknowns to deal with. So rather than setting up two unknowns, I'm going to instead cross this out, and I'm going to call this one total 12 minus part is equal to this one, from here to there. So this is a segment addition postulate. So this brown portion here is going to be 12 minus x. So instead of calling this y, I'm calling it 12 minus x. And the reason why I want 12 minus x is because we can set up a Pythagorean identity for this one. So if we kept this as a y, then you're going to have y squared plus x squared equals hypotenuse squared. And then you would notice that this is only one equation. It would have two unknowns, which is unsolvable unless you have another equation. Which technically, you could just... Alright, let's talk about this. So if you arrive at this particular point, then x is here, x is there, and then y is there. So unfortunately, this is only one equation. You'd have to do this one right here. You'd have to say, oh, y is actually equal to... is equal to what? It's equal to 12 minus x. So let's go over this one real quick. So the totality, the total length of this is going to be 12, but 12 is the sum of this segment plus that segment. Segment addition postulate. And then you could solve for y. So y is equal to 12 minus x. So you take that, and then you could substitute that back in. Which, you know, it's perfectly fine if you want to use that strategy. But I guess in a way the prior setup for this one, if we rephrase this as y directly, in a way we've already done the substitution in the first place. So again, rather than calling that length is equal to y, we're going to call this length is equal to 12 minus x. So, are we doing something totally novel compared to the one I just erased? Not really. It's just skipping the writing of the letter. So again, calling this brown, or whatever this muddied red is equal to 12 minus x, then we could set up a Pythagorean identity for this whole portion right there. So let's extract that just to clear the visuals. So again, the hypotenuse of this triangle is going to be 4 root 5. This muddied red thing is going to be 12 minus x from segment addition postulate, and then this side here, short leg is going to be x. Alright, which means we can, well, let me call this one alpha first and call this one 90. Alright, so since this is a 90, this is a right triangle, we can therefore set a squared plus b squared equals c squared. So 12 minus x squared plus x squared is equal to that one squared. Again, a squared plus b squared equals c squared. Alright, just to make sure things are clear, I'm going to drop the color at this point. Let's take square root of both sides. Square root of that, square root of that. And resolve this binomial expansion. So we're going to get negative x squared is going to be x squared. And then don't forget the algorithm. First one times second one times 2, which is negative 24x. Lastly, we have 12 squared, which is 144. That one's easy. So that is the entirety of the left-hand side. Right-hand side, we just clear the squaring by applying the square root. So it becomes 4 root 5. Since we're working with actual distance, we drop the negative. Alright. Actually, I didn't even need to say that. Forget that. Okay. So here we have the situation right there. Is that what I wanted to do? I think I shouldn't have taken the square root. Okay, that's okay. Whatever. So this one right here. Yeah, I should. I think I jumped the gun. Okay, that's okay. That's fine. That's fine. That's fine. It's not too bad. I should not have taken the square root of both sides. You know what? I'm gonna undo it. I'm sorry. Let's undo that, but keep the same work though. So I'm not going to apply the square root to both sides because that's gonna be counterproductive. So let us not take square root of both sides because we're not solving for the hypotenuse this time. Yeah. Why am I mixed up today? Okay. So again, we're not taking the square root of this one because that one is actually a value. We're not trying to solve for a letter inside here. So the derivative property of exponent, we're going to get 16 times 5. Because this ends up being quadratic, so we don't need to do that nonsense. So this is x squared, x squared. So let's start collecting like terms. That's going to be 2x squared. Nothing there. That's 144. Is equal to 2. That's 30 plus 50 is 80. All right. Everything is divisible by 2, but let's subtract 80 from both sides. So minus 80 minus 80. And then let's divide all terms by 2 to make the quadratic even easier. So divide by 2. It's 1x. Divide by 2 is negative 12x. Divide by 2 is positive 32. Okay, well, this is a factorizable quadratic. Quadratics will always pop back up. So factors of 32 to sum it to be negative 12. It's going to be 8 and 4. Signs are the same, both signs are negative. So thus we have two answers. X is equal to 4, comma 8. That's kind of weird, right? Shouldn't we just have one length for this one? Well, it's because this drawing is actually technically ambiguous with these numbers, but, and I'm trying to be very emphatic there, this x value is less than this value right here. So what I'm trying to say is, by the visuals, if you trust the visuals to a degree, we can see that this x is less than this one. So let me write that down. So 12 minus x is this brown, muddy red looking color. That's going to be greater than just this length right here. So we'll see which of those values will this one be true for, right? So if you plug in 4 into this x and 4 into that x, we're going to get 8 is greater than 4, which is true from the visuals. If you put an 8 into there and 8 into there, we're going to get 4 is greater than 8, which is not true according to the visuals. So therefore, just by the visuals, if we trust it enough, we will go with this answer rather than the 8. Alright. So what do we have at this point? We know that x is equal to 4. What does x mean? X means this particular length right there. So now we know that length is 4. And since we know that, we can solve for this. We can figure out what the length of that side is. So 12 minus 4 is 8. But let's not lose sight of what we're supposed to do. We're supposed to do tangent of alpha. That's this angle right there. Okay, it's doable. We have all our sides at this point. So from the perspective of angle alpha, tangent is going to give us the ratio of opposite 4 over adjacent 8. Which simplifies into 1/2. Always a reduced ratio in the end. So don't forget tangent functions. All trig functions will give us reduced ratios. So tangent of alpha is equal to 1/2. And we are done with that particular problem. So that was quite a bit of work. I'm not going to go over a recap since I technically already went over a recap in the middle of the problem. But you know what? Let me do it anyway. Too bad. So just to recap all the way from the beginning, we figured out that this thing here is a square. And then after that, we determined that this triangle here is congruent to that triangle there by using the old geometry properties. And once we determine the congruency of those triangles, we set letters so that we have fewer letters to work with. So if we set this as singular x, then this one we could set in terms of x, which would be 12 minus x. And then we notice that this is a right triangle, so we can extract that to here, and once you get a right triangle, since everything is in terms of x, you can solve for x using a single equation, which is going to be the Pythagorean identity. That's what we did for this problem. Final answer, 1/2. I feel like I'm worse at explaining things today for some reason. Okay, well, that's it for the problems on this sheet. We are approaching the end with great rapidity. So let's do a couple, maybe 3 more problems for this set. Alright. Let me think about the order for this one. Yeah, let's do this one. Yeah, let's do this one first. That's fine. Alright, there it is. We are given this is angle beta. This is going to be 90 degrees. This is given as 90, this is given as 90, and then we are informed that this here, the length here, is congruent to the length there. So in other words, if we call this one M, then M is a midpoint of AB, of BA. Just to make things clear. Stick that in, toss it to the side. Okay. And there's one more piece of information we are given. It's going to be cosine of beta is equal to 1/2. When we write beta, it's not going to be the typical B. It's going to be the B with the extended back like this. There's like a little tail right there. So cosine of beta is going to be equal to 1/2 according to the given. And then, ooh, there's one more given I missed. And the other given is this one's going to be 2. And then the question is, what is the perimeter of the figure? So let me fill this out. This is going to be C and this is going to be D. So the question is, what is the perimeter of figure ABCD? Okay, so a few things to make note. So that's the problem, and what are we given? In order to figure out the perimeter, we need to add this side plus this side, which we know, plus that side, which we don't know, plus this side, which we also don't know. Alright, but here's the thing though. We know that this is 2. This feels like a rectangle, doesn't it? But let's not go off of suspicion. Let's go with confirmation. Since this is 90, then by supplementarity, this is also 90. Since we have 3 angles that are 90, then by sum of interiors, or a quadrilateral, this one must also be 90. So yes, this is in fact a rectangle. Since this is 2, then therefore this one right here is also 2. Since this is a midpoint, we know that this from here to there is 2, then from here to there is also 2. Okay, so that's a bunch of stuff from figuring out that this is a rectangle. What else do we know? Well, we've exhausted this number here and the fact that this is a rectangle. So let's move on to this given information. Given that the cosine of beta is equal to 1/2, well, where are we looking? Right here. And cosine gives us the ratio of adjacent relative to hypotenuse. So this hypotenuse, we don't know what it is. But hey, we're given the ratio, right? So let's call this h. That's going to be h. This is a ratio between this number here and that number there. So we can equate this one. This is the proportion of 2 to h. There's the proportion. All we need to do is solve for h. Cross multiply is very straightforward. H is therefore equal to 4. So let's cross this out and we'll call it a 4. Very nice. Okay, so unfortunately we still can't answer the question of the perimeter, because now that even though we know what this hypotenuse is, it's 4, we know this is 2, we know that is 2, and we know that is 2. Unfortunately, we don't have this length right here, which means we need to figure out what this one is. And since we have two sides known for a right triangle, therefore we could use the Pythagorean identity to figure out this last side. So let us do that. So what is this thing right here? I'm just going to arbitrarily call it y. Set up the good old Pythagorean identity. So a squared plus b squared. I'll try to keep the colors consistent. That should be equal to hypotenuse squared, which is the 4. Alright, so a bunch of known values. There's only one thing we don't know. That's the y. So we could easily solve for that. So this is going to be a 4. This is going to be a 16. Subtract 4 from both sides. Subtract 4. Clean up step. We have y squared is equal to 12. Taking the square root of both sides, y is equal to, which is equal to 2 root 3. So y value is 2 root 3. Since this is 2 root 3, then because this is a rectangle, opposite sides are congruent, this one here is also 2 root 3. And that gives us the final side. All we need to do is summate all the sides to get the perimeter of ABCD. So in other words, that's going to be 2 plus 2. Let me use the colors. So we have 2 plus 2. And then we have the hypotenuse of the triangle, which is 4. We have the given side, which is 2 up there. And then we have the final side that we figured out, which is going to be 2 root 3. And all we need to do is just collect terms as much as possible. So this is going to be a 6. 6 plus 4 is 10. That's a radical. It's uncollectible, so we're just going to leave it split up. And that's going to be the perimeter. We don't know the units, so we're just going to call it units. Final answer for the perimeter question right there. So that's the answer, but in review, we were given this 2 initially. We figured out that this whole thing is going to be a rectangle, so therefore if this is a 2, then this one's a 2. Since this is congruent to this one as a given, then we know this one here is also a 2. Because we're given this ratio that's relating this adjacent to that hypotenuse of 1 to 2, then this one is half of the hypotenuse. So therefore, if you double this, then you get to the hypotenuse, which is 4. Once we figure out this is a 4 and we have this 2, we can use Pythagorean identity, a squared plus b squared equals c squared, thereby allowing us to solve for y. Once we figured out the y was the 2 and root 3, since this is one part of a rectangle, then the opposite side is also 2 root 3. all the numbers are known. Just simply summate all of them to get the perimeter right there. All right. Do I want to do more problems? I feel like I wanted to move on to something else, so I'm actually going to move on. I actually have 2 more problems written, but let us not do that for now. Let's go back to the idea of radians and degrees, right? And for the most part, for the problems we've been working with, we've been dealing with triangles that are only in the, what's it called, quadrant number 1 for xy plane coordinate. So let me show them. Let me show you what I mean. So here is the x-axis, and then here's the y-axis. So when you see something like pi over 3, you see something like pi over 4, you see something like pi over 6, those are all specific angles. And let me give the corresponding degrees for this one, which my advice to you is to memorize these. So this one is going to be 60 degrees, that one is going to be 30 degrees, and then this one is going to be 45 degrees. So further differentiating them, let's color this as the red one, right? So if you're looking at this particular angle here, here's how it works when you're dealing with the xy coordinate plane. We always are going to be starting off here. This is by convention. I guess it's kind of weird, right? Like what do I mean by starting right there? So just to ground the situation in a more concrete, with a concrete idea, let's just pretend that we're going to be growing a hypotenuse. And the way we grow a hypotenuse is we start from the origin and then you extend it in a certain direction. So if I stop here, for example, at 1, then this hypotenuse length is going to be 1. But what I'm going to do with this hypotenuse length of 1 is I'm going to rotate it 60 degrees. So again, take this one right here, 0, 0. If I leave it at 0, 0, then the hypotenuse is 0. But we're not interested in that. So if I, again, start at 0, 0, I'm going to grow a hypotenuse. I could stop at 1, or I could stop at 2. So I've grown this hypotenuse length of 2. What I'm going to do is I'm going to rotate it. I'm going to give it 60 degrees. So what that means is once I grow this hypotenuse length, I'm going to move it counterclockwise in this direction, 60 degrees. So again, I'm growing a hypotenuse length of 2, and I'm going to swing it in this direction, and I'm going to stop here. So again, that length was 2. What do I mean by 60 degree swing? It means from the starting position by which I've grown this hypotenuse, I'm going to move it on this pivot point right here. This one is anchored at the origin, and this one is free to swing around. So again, grow a hypotenuse of 2, and then rotate it 60 degrees right there. Full circle from here to here will be 360 degrees. All right. I don't know if that's clear at all, because again, there's no feedback. Yeah, this is 60 degrees. We get a point right here. Let me think about if that's what I wanted to say. Yeah, that's exactly what I wanted to say. So it doesn't have to be a hypotenuse length of 2. I'm going to set it arbitrarily. So let me restate that again. But what I've stated so far, nothing's wrong with it. It's exactly what I wanted to say. But I want to be more generic. So rather than specifying a hypotenuse length of 2, I'm just going to call it something like h. So here's the steps again. You grow a hypotenuse length of h, and then you're going to swing at a certain number of degrees. It's going to be 60 degrees. How do I know it ends up right here? Well, number 1, I have experience, and then number 2, let me explain this whole system again. So from here, full circle degree is going to be 360 degrees. And you notice that there are 4 zones, right? Since the x-axis is perpendicular to the y-axis, this is 90 degrees. That's 90. This one's 90. That one's 90. That one's 90. If you summate 4 times, if you do 4 times 90, that's 360 degrees. So one of these corners is 90 degrees. So if you grow a hypotenuse and you swing it 90 degrees, then you end up right here. The hypotenuse that you've grown ends up right here. But we're not swinging at 90 degrees. We're only swinging at 60 degrees. So pivot point, grow your hypotenuse, end point, that's how long the hypotenuse is. We're going to swing at 60 degrees and right here. So pivot point is at the origin. This is where we rotated the point. Alright, so that means from here to here is 60 degrees. This is not a triangle. Here's how you form the triangle by convention. You always, once you finish swinging the hypotenuse, you draw a line straight towards the x-axis. Always straight towards the x-axis. Never to the y-axis by convention. Always directly to the x-axis. And by directly, I mean the shortest distance possible. So you're not doing something like this. You're always doing it straight towards the x-axis, which means it's going to be 90 degrees. Thereby forming a right triangle. It has to be a right triangle because we're dealing with trig functions. At least for now, it has to be a right triangle, right? Okay, so that's the convention we're going to follow. So, in review, you grow your hypotenuse. How long do you need to grow this hypotenuse? Well, it depends on the problem. So if someone told you the hypotenuse length is 2, then you go from 0 and you grow it to x coordinate number 2. And then you look at the degree specified, it's 60 degrees, so we're not finished graphing, we're going to swing it over right here. So this length of 2 that we've just grown, it's moving from this the standard default position to this new position, 60 degrees. So there's that. And then from this length, we're going to form a right triangle in our mind's eye, or just visually, to solve problems. It's pretty abstract, honestly. So you're going to drop straight from the point that has the final location to which the point has moved right here. Drop it straight towards the x-axis. And again, by straight, it has to be 90 degrees. Alright, so there it is. So once you notice that, there are a few more things to make note of. So this point here, don't forget this whole system, this xy coordinate system, it's xy coordinate system, rectangular coordinates. So the rectangular coordinates of this one, we have 2 points. It's x, comma, y. What does that mean for us? Well, let's just finish coloring this triangle. So this part right here, I'm going to color it as this green color. If you think about it, this is just a rectangle. And since that's a rectangle and this is rectangular coordinates, then all you need to do is figure out the lengths of the dimensions of this particular rectangle. So from here to here, if this is x, then that's green x. And this blue thing, that's just literally the y coordinate of this particular point. So I guess that's it for the situation in terms of forming a right triangle given a very abstract angle. Oh, I should specify this. This 2, what does that 2 mean? That means the hypotenuse is 2. So radius of the triangle that we're drawing is going to be radius 2. Or hypotenuse, I mean. You're going to see this is going to be interchangeable. You might see the letter R to represent radius because this is technically a circle looking thing. But kind of generically, we'll just call it H. H for hypotenuse. I'm going to stick with H for now. Just be aware that I might swap between R and H. Alright. Okay. So this whole thing is to, if you follow the instructions specified here, it leads you to the formation of this triangle there. That's all I wanted to say. And let's do another one. Let's look at this one here. So I'm going to do a new XY coordinate system for this one. So pi over 6, if you translate it from radians to degrees, that's the degrees. Here's the y coordinate. Here is the x coordinate. Let us specify a hypotenuse of 1. So what that means is we're starting from the origin. We're going to grow in the positive 1 direction on the x-axis. Right there. That's 1. So from this instruction, we get this thing right here. And then, because of this angle instruction, we are going to rotate this thing counterclockwise by convention. If you just see this as a generic positive number, then you rotate it in a counterclockwise fashion. So let me specify that. By convention again. That's one you just have to memorize, unfortunately. We're going to rotate this one 30 degrees. Hypotenuse 1, rotate 30, ends up right here. How do I know right here? Because again, from here to there would be 90 degrees. This is less than 90 degrees. So visually, I want it to be like about a third of this entire angle. Because again, if this angle here is 90, then a third of that is going to be 30. So this is just an eyeball drawing. 30-ish. 30. Alright. So what that means is we also have XY coordinate systems right here. This is, if we call this one the x-axis, then this one's going to be the y-axis, the y coordinate. For what exactly? For the point right there. Okay. So this situation is specified from these set of instructions right there. So what is this one doing right here? Drawing the XY coordinate system again. Here's the y axis and then here's the x axis. This is 45. And we're going to specify a hypotenuse length of what to do? Let's just do something vague. Let's just do r. So nothing specified. I'm not specifying any specific length. So let's say r. So what we do is we're going to grow a hypotenuse from 0 to r. Again, it's unspecified. And we're going to swing it 45 degrees, which is half of 90 degrees. So from here to here-ish. So again, grow the hypotenuse length of r and then rotate it halfways. It's right there. That's a 45-degree angle. It's right here. And of course, the thing has its own XY coordinate system. So from here to there, we can call that one x. And then from here to there, that is the y. And that leads us to this particular coordinate. So this thing right here is the right triangle that's specified by these set of instructions right there. Okay, so those are the conventions to follow. So I'm just basically, this doesn't have to make sense. It's just basically the conventions that we're going to be following when we are generating a triangle, a right triangle in our mind's eye if we're given specific angles. We already know how to do this from prior situations, but the reason why I'm introducing this on the rotating as an idea of rotation is because now we're going to deal with angles that are not 30 degrees, not 45 degrees, and not 60 degrees, but they're very closely related to those particular angles. So, for example, right, what if we're now given something like 130 degrees? No, I'm sorry, 150 degrees. So at the moment, from the prior stream, we don't have the tools in order to work with this. So if I'm asking, for example, what's cosine of 150 degrees? What we've covered so far is inadequate to answer this question. Because we only worked with 30 degrees, we've only worked with 60 degrees, 45 degrees. That's it. That's all we have to work with. Well, this one isn't very far removed from those particular values. So this one right here, let's just get... It's hard to generate this triangle in our mind's eye, so hence this whole system that we're going to follow right here. So 150 degrees. So we're going to put the x-axis here, and then we're going to put the y-axis here. This thing right here, right? Well, there are two things it specifies. It specifies a radius, which, it doesn't give us anything, so it's a vague radius. I guess you could say it doesn't really specify a radius, but that's okay. It's implied that there is some sort of radius, some sort of hypotenuse thing. We don't know what the length of this hypotenuse is, but we're going to grow the hypotenuse up to from here to there. And then what's going to happen is we're going to rotate that a certain number of degrees. How do we rotate it? 150 degrees. So where do we end up rotating this particular hypotenuse? Well, from here to there is 90 degrees. This is greater than 90 degrees. So we're actually going to finally break past this particular checkpoint. So where do we end up? Here? No, we don't. And why not? Because this is 90 as well. So from here all the way to there is going to be 180 degrees. This is 150 degrees, which is 30 degrees short. And that's going to be a key number. It's 30 degrees short of half circle. So how do we swing this hypotenuse that we've grown? We're going to swing it all the way right here. How do I know right here? Because that's going to give us the deficit of 30. So let's talk about that again. So the entirety of this thing is half circle, is 180 degrees. The specified angle is 150. So from here to somewhere here-ish, right? So if you do the angle addition postulate, since the total angle is 180 and then the partial is 150, then the remainder right here is going to be 30. There it is. So again, just angle addition postulate with supplementary angles. So this whole thing, given from a problem, is 150 degrees. It leads us to this thing right here, following this convention of drawing this triangle in our mind's eye, or literally on paper. But this ain't a triangle though, right? It's just going to be a stick of a hypotenuse. So what you need to do is you need to drop it down from this one straight down to the x-axis. So from here to here. Alright. Now that forms a triangle, right? Let's take this one and isolate it real quick. So if we take this triangle, let me copy paste it. We have the tools. Copy paste. And there it is. So why do we go through all this trouble, right? Just to form... Don't we already have a 30, 60, 90 in our head? And yes we do. But it'll be a lot faster once you kind of understand what's going on. But the main idea is, from this 150 degree specified into this trig function, we can generate this particular triangle. Okay? But what are the ratios of a 30, 60, 90? Since this is the 30, the smallest angle, it opens up to the smallest side ratio, which is 1 ratio. And then, since this is the 60 one, by complementarity, then it opens up to the root 3 side. And since this is the 90 degree, it opens up to the 2 side. So 1 to root 3 to 2. Those are the ratios for a 30, 60, 90. And you might be wondering, wait a minute. we already knew how to draw that. We don't need this whole clunky system, and we actually do need this clunky system because XY coordinate system has positive, negative signs. And here's the reason why. So from here to here is going to be positive x direction, but from here to there is negative x direction. And then for the y values, from there to there, positive y values, and from there to there, negative y values. And here's where it's going to get kind of strange. You see this root 3? That's actually a negative root 3. And then you might be wondering, wait a minute, why do we have a negative distance? I thought distances weren't negative. And that's true, distances aren't negative, but for purposes of calculating this one, directionality does matter, and the negativeness specifies a direction. Yeah, so is that kind of a answer? I don't know. Hopefully that's a satisfactory answer. So that's why simply memorizing the special right triangle is insufficient. So if you just memorize 30, 60, 90s, and you're like, oh, this is 1 to root 3 to 2, unfortunately it doesn't help us here because this one, the fact that it is 150 degrees, which is none of those, which is not 30 degrees, it's not 60 degrees, it's not 90 degrees. This one right here means that there are going to be positive, negative signs we probably need to contend with. If we just assume all these positive ratios, positive 2 to positive 1 to positive root 3, we're auto-assuming that we're forming a triangle in this particular sector or quadrant of this triangle that we're forming in our mind's eye. So this is called quadrant 1. What this one actually specifies is a triangle, right triangle in quadrant 2. So again, it might seem confusing, but it's just a bunch of conventions we need to follow. Alright, so we haven't quite answered this question yet, right? So the question is, what is cosine of this particular triangle of 150? But 150, it doesn't form a right triangle. So we have to instead form a reference triangle, right? Because 150 is ultimately the angle we're staring at. But 150 cannot be an angle inside a right triangle. So let's take a quick look at that. So 150, this is going to be 90 degrees. This is going to be past 90 degrees, which is what 150 is. So can we form a right triangle from this one? No, we can't, because this one needs to be 90. Sum of interiors, if this is going to be 150 degrees, and this is going to be 90 degrees, 90 plus 150 is 240 degrees. That's not a right triangle. That's not even a triangle, because it fails a sum of interiors. So to circumvent this weird situation where we can't generate a right triangle using this 150 degrees, we have to generate a reference triangle. So this is not our true triangle, right? It's just going to be this kind of scaffold so we can mechanically do the problem. So again, this is called the reference triangle, with this reference angle right here of 30 degrees. So this is not our true problem. We're not looking for a cosine of 30 degrees. We're looking for a cosine of 150. But it's related to this 30 degrees right there. Alright. Once we establish where the reference triangle is located, we need to keep track of the signages. So again, it's standard 1 to root 3 to 2 ratio 30, 60, 90, but taking into account the negative directionality, this side, this quote-unquote side is negative root 3. Let's take a quick pause to take a quick breather. What are we answering? What's cosine of 150? So we're looking at this triangle as a proxy for 150, which is right there. So what is cosine of this triangle? Again, we're focusing right here on this 30. Cosine is what? It's going to be the ratio of adjacent over hypotenuse, and the adjacent is negative root 3 over hypotenuse of 2. And this is the answer for this particular problem. I feel like that was like a lot to talk about, but like I said, it'll become a lot easier once you go through the motions. So let's just do a bunch of problems, and that will hopefully get us acquainted with the system. And once you're well acquainted with the system, you're gonna feel a lot more comfortable. It's not gonna look so foreign. All right. I don't think I did a particularly good job at explaining that. I felt like I was a little scattered, but that's okay. Maybe I'll clarify it in a future stream or something like that. Okay, but let's do a few problems. So let's do sine of 135. What is that equal to? And then we're going to do tangent of 100. What's that? 180 minus 60 is 120. Yeah, we didn't do that one yet. Let's do sine of what are we doing? $2.25. And then lastly for the set, this will be cosine of 240. Alright, so here are 4 problems. So the question is, how do we do this particular situation? Well, this is not one of our favorite angles, right? Our favorite angles are 30, 60, 45. Any of those numbers, we could easily draw the reference triangle. We can easily form the triangle in our mind's eye. We can draw in any order we wish, and it's not going to matter, right? So if we're doing something like sine of 60 degrees, technically this is sloppy. You just draw like a triangle like this, orientated in however we wish. So you can draw like something goofy like this. So 60, you could label it here, and then 30, this has to be the 30, this has to be the 90. What are the ratios of a 30, 60, 90? Smallest angle opens up to 1, medium angle opens up to root 3, 90 degree opens up to the 2 side. And now we can answer the question, right? So from this perspective, opposite is root 3, hypotenuse is 2. And that's how we answer this question. This is technically sloppy. So let's be a little more careful in the situation. So again, these ones are the perfect numbers. These are very easy to deal with. But we don't have those numbers directly anymore. Instead, we have 135. So let's figure out how to do this. Following convention. Y-axis, x-axis. There's going to be some sort of hypotenuse we will grow. We don't care how long it is because sine functions will give us reduced ratios. So the actual length of the hypotenuse that we are growing, it doesn't matter. So unspecified hypotenuse h. What we're going to do with this hypotenuse h, we're going to swing it 135 degrees counterclockwise by convention. So take this one and swing it, that's 90 degrees. We want 135. So keep going. Swing it here. No, that's too far because this is, again, 180 degrees. This is only 135. So where do we swing that one, right? In order to mathematically determine, that's half circle. We don't want to go that far. So if you find a difference, then it's easier to draw, right? So 180 minus 135 is 45 degrees. A familiar face, right? 45 degrees. So that's going to be something called the reference angle. So again, grow hypotenuse, swing it 90 degrees, swing it 135, ends up like right here, halfways. So again, this is the pivot point. We're going to swing it like that. So what has happened? Well, all we have is a stick. We don't have a triangle. So we're going to have to manually take this one and drop it straight towards the x-axis to form 90 degrees. And once we have that, we also have an adjacent here to here. Following conventions, right? This is the x-axis. Positive direction, negative direction. So whatever value, whatever x value it is, it has to be negative by assignment. You know, again, it specifies directionality. And what's this? Well, y-axis here is positive, y-axis there is negative. So this goes upwards, so this is plus. Alright, so now we know that we're looking at this particular situation. The reference angle is 45, so this is our true angle. It's going to be 135. But 135 doesn't work for a right triangle, so we force it as a proxy by referencing this right triangle. And that triangle right here that we're referencing has a reference angle of 45 degrees. So this is something we can work with given our tools as of now. What are the ratios of a 45, 45, 90? Because if this is 45 and we deliberately formed a right triangle right here, this should also be 45. Our good old buddy 45, 45, 90. So following this orientation of the drawing, 45, 45, 90. What are the ratios? It's going to be 1 to 1 to root 2. But the orientation is now coming into play. This is negative x value. So we put a negative right here. And that's the only thing this concept drawing has done for us, is to give us this -1 value. If you memorize this, actually, let me not emphasize that. Yeah, there are ways you can circumvent having to do this. If you memorized a mnemonic, all students take calculus, but let's not talk about that. But just understand what this one is doing. This is just a system to get us signs, the correct signages for the actual angle, not the reference angle. So to reiterate, this one is not actually 45 degrees, because 45 degrees, if you just take this one and you form the right triangle in your brain, you're forming this one. 45, 45, 90. Everything is positive, and that's going to lead us astray. So this one is not 45 degrees. It's 45 degrees short of 180. And 180 takes us into this particular sector or quadrant where the x values are negative, but the y values are positive. All right. Okay. So referencing this proxy drawing for the triangle that we're supposed to have in our mind's eye, what's going to be the sign? Sign is opposite over hypotenuse. So we didn't even need that negative sign. So 1 over root 2, and that rationalization is equal to root 2 over 2. So that is the answer for this problem. Okay. It feels slow now, but eventually we'll just cruise through those a lot faster. So I'm already drawing the xy coordinate system. What are we looking at? We're looking at 120 degrees. Right there. So grow the hypotenuse. So we get 90 degrees. We're not 90. We're not 180. We're between 180 and 90. So somewhere here-ish. Where exactly are we? We are right here. How did I know that? Well, here's 120, right? It has to be, it's a certain degree short. How many degrees is it short of a full 180? It's 60 degrees short. So visually, I'm used to drawing 60-degree angles, so I know to draw it relatively like right here-ish. So there's a triangle. Well, actually, this is just a stick, right? We've just grown the hypotenuse. To finish the construction of the right triangle in our mind's eye, drop it straight down 90 degrees. Make note of a few things. This is going to be positive for the y value, but negative for the x value. And that's it. That's all we care about. This whole drawing is, again, just for getting the signages for our reference triangle, which is not a true triangle, but just a reference triangle. Let's draw the reference triangle, keeping these signs in our head. So for a 30, 60, 90, this is root 3, this is 1, this is 2, 90 degrees. This value here must be negative because it's going in the negative x direction. So that the only thing that does is makes this into a negative. Y value, still positive. What does that mean for us? We can now take tangent. So tangent of this reference angle is going to be opposite root 3 over adjacent negative 1. See that negative 1 difference? There it is again. And that's the final answer. Well, I'm sorry, we should probably clean this up. It becomes negative root 3. Final answer. So a little faster than before. Again, it's just a system. This one's a little more complicated now. It's actually past 180 this time, but it's okay. We're going to do the exact same thing as before, pretty much. Alright, number 1, grow your hypotenuse. Number 2, swing it until you swing it this many degrees counterclockwise. So if you grow it here and then you swing it up to here, that's 90. This is shorter than 180. This is 180. 225, it's past 180. So we're actually in this particular territory. How far are we into this territory? Well, if from here to here is 180, then we have a little bit left over, right? What is that left over? Just do subtraction. It's 45. So we're pushing past 180 degrees by 45 degrees, so we end up right here. So grow the hypotenuse, swing it 225, we end up right there. So let me clear the visual clutter. So again, grow the hypotenuse, swing the hypotenuse 225. How do we know that's 225? Because this is 45. Because 45 degrees plus 180 takes us back to 225. So the hypotenuse stick ends up right there. That's not a triangle. So forming a triangle, just draw it straight towards the x-axis. 90 degrees. Well, my coloring system is messed up. Let me put a different color. Okay. Alright, so a few things to make note of. We do have an adjacent here. We have a x length. It's in the negative zone. This is the origin. This is positive x. That's negative x. So this, whatever value we find here, we have to assign it negative for directionality. And for this one right here, because this is our y-axis, and this is going below the x-axis, therefore this one is also going to be negative. So that's a negative value, and then that will be a negative value. Now let's draw a reference triangle, extracting this one. What are we referencing? 45, 45, 90. So 45, 45, 90. What are the ratios? It's 1 to 1 to root 2. But because of this modeling, we know that this is going to be a negative assignment. And this is also negative. So 2 negative values to account for. Alright, and then now we could just use this reference angle. So we're looking at this reference triangle as a proxy for this one right here, right? So what's sine of this particular angle right there? It's going to be relative to this one, it's opposite negative 1 over hypotenuse root 2. Rationalizing. And then we're done. Alright, moving on to the final one of this particular set. This one is not one of our familiar faces, at least not directly. It's not directly 30, 60, nor 45. Also make note that it's past 180 degrees. So let's draw it out right here. Y-axis. x-axis. This is 240. So we are going to grow a hypotenuse, and we're going to swing it 90 degrees, 180 degrees. That's too far. This is 270 degrees, right? Because this is 90 plus 90 plus 90. It's 270. This is less than 270. So we're like right here-ish. How did I know we're right there? Well, again, figure out this one. That's 180, right? So if you subtract 180 to travel from here to here, the remnant is going to be 60 degrees from here to there. So that's how we know. The hypotenuse stick ends up right here. And now all we need to do is complete this proxy for the right triangle. So take this one right here. Always direct it towards the x-axis straight as possible. 90 degrees. And then of course we have the adjacent right here. To complete the right triangle proxy, make note of the directionalities. X-axis is in the negative direction for the x-axis. Y-axis. This is below the x-axis, traveling downwards, so this value is also negative. Alright. What is this angle again? Well, again, from here to here is 180, from here to here is 60, so 60 degrees is our reference triangle. What are the ratios for a 30, 60, 90? Well, 1 to 2 to root 3. Let's reconcile these ones with our signages we've just determined. So this is negative and that's negative. We now have our reference triangle completed. Let's take the cosine of this reference angle here. What is cosine? Adjacent over hypotenuse. So I know I said that this is an unspecified hypotenuse, but remember these are just simplified ratios. Whole number reduced ratios. So I'm not saying that the hypotenuse length, I'm not committing to the idea that the hypotenuse length is 2. This is just a ratio. The cleanest ratios we can possibly get. So I could write I could write negative 2 over 4, but that's being a little presumptuous. So by putting negative 1 over 2, I'm implying that this is simplified. It might not actually be the lengths, it's just going to be the reduced fractions with an unspecified hypotenuse length. Okay. Well, we might as well do one more, or maybe several more, right? So let us do tangent of something like 300 degrees. You knew this was coming, right? So this is now 300. Well, XY coordinate system sketch first. Figure out which quadrant we're in. This is 300. So this is 90. This is 90. This is 90. So from here to there is 270, right? And this is past 270. By how much? 30 degrees. So the hypotenuse stick ends up right there. Okay. What else do we know? Well, right here is 30 degrees, but you never form the right triangle like this one. It's always towards, you always drop it from the pivot, from the swung point directly towards the x-axis right there. Not to the y-axis, always to the x-axis. So that one to there. If only I could draw, right? Okay, right there. Completing the triangle with the 90 degrees right there. Okay, so what do we know about this particular triangle? Well, from here to here, that's 30, but that's not contained in the reference triangle. So this is 30 degrees. But since this whole thing is 90 degrees, then by complementarity, this one must be 60. Alright. And let's just make note of the sign directionality of the situation. So this is in the positive x direction. So whatever value we find for this one right here, we're going to assign it positive. And this is going downwards along the y-axis. So this is negative by our assignment. So what's the proxy triangle? Let's draw it. So extracting the proxy triangle, the reference triangle, something like this. That's a 90, this is the 60, and this is the 30, right? What are the ratios of a 30, 60, 90? 1, root 3 to 2. That's a negative downwards, so this is negative on the root 3. That's a positive, so this one we'll keep it unchanged. Now we can take tangent. Tangent is just the ratio of opposite relative to hypotenuse from the 60 degrees. Remember, the 60 is the reference. So opposite over adjacent. Simplify. And we're done with this particular problem. Good to go. Let's do some random ones at this point. So let us do cosine. Cosine of what? 210. So must we draw out the entire thing always? No. It's okay. As long as you memorize it's always memorization, isn't it? So here's how you can remember things, okay? If the angle in here is 90 or less, you're right here. This is 90 degrees. So if you're doing something like cosine of 30 degrees, then the triangle we're referencing is right here. Well within here. This is positive x direction, positive y direction. So whatever ratios you find, whatever trig ratios you find here, there's all going to be positive over positive. If you're looking inside a trig function and inside the trig function is less than 180 but greater than 90, so like for example something like 120, then you're past the 90 degrees but you're before the 180, so it's somewhere here-ish. So if you are in this particular quadrant, this is called quadrant 2, then the x coordinate values will be negative and the y coordinate values will be positive. So in this situation, some of your trig functions are positive, will give you positive ratios, and then other trig functions will give you negative ratios. So if your angle degree in there is greater than 180 but less than 270, because this is 270, then you're within this particular quadrant, referred to as quadrant 3. So something like 225, which means that the x coordinate will be negative, and then the y coordinate will also be negative. So some of your trig ratios will be positive, and then some of your trig ratios will be negative. If this particular value here is greater than 270, but less than 360, you're somewhere here-ish. Because this is 90, that's 180, 270. So if this is something like 330, then your triangle, reference triangle, is somewhere right here. So if that's where your reference triangle is, make note that you have a positive x coordinate system, and then you have a negative y for the directionality. So some of your trig functions will be positive, and then some of them will be negative. And that's basically it. So if you really want to, I'm not going to emphasize it at the moment, but if you really want to, you can memorize all students take calculus. That's a mnemonic that some people use. Who cares if it's true or not? It's just a nifty little mnemonic to help you memorize some things. So what does this mean? All trig functions are positive in quadrant 1. Quadrant 1 is just the neutral start position. And then here, students, well, the S is for sine, so all sine functions are positive right here. All other functions are negative. And if you're in quadrant 3, only the tangent function is positive. All other functions are negative. And if you're right here, only the cosine function ratio will give you positive. All other ratios are negative. You don't have to memorize it. It's a nifty little trick. It will help expedite the process so you don't have to draw the system the entire time. But we're going to emphasize drawing first. Okay, so where are we? We're going to be in quadrant 3 because that's past 180. So from here all the way to right here. So the triangle is like this. It has a negative adjacent. It has a negative x coordinate and it has it has a negative y coordinate as well. So whatever triangle you draw, that's what we're going to do. And you notice how fast that was now, right? So this is going to be 280. So from here to there is 180. So what's the leftover? What's the spillover? The spillover is 30 degrees. So this is going to be 30 degrees. This is not drawn to scale. You don't have to draw it to scale, but it's nice if you do. So this is the triangle that we're referencing. This is the 30. It opens up to negative 1. It has a negative root 3 adjacent from this perspective. And then hypotenuse, almost always going to be positive 2. There it is. What's cosine? Adjacent over hypotenuse. And then we're done. Let's do tangent. Tangent of what? 45 degrees. Easy problem, but make sure you revisit easy stuff. So what are we doing? We have 45, that's less than 90 degrees, so we are well within quadrant 1. So this is our triangle. It's positive in this direction, positive in that direction for the right triangle. So 45, 45, 90 is going to be positive 1, positive 1, positive root 2. Tangent is relative to right here. That's the eyeball. So tangent is what? Opposite over adjacent. So done with that problem. We're going to do sine of 300 and just 300. What are we doing? Well, which quadrant are we ending up in? 90, 180, 270, 300. So we're here-ish. Quadrant 4. What's happening in quadrant 4? This is not drawn to scale. Always connected to the x-axis. So we have a positive for the x-coordinate and a negative for the y-coordinate for our reference triangle. What is our reference triangle? This is 270. This is 30. So this angle here is complementary to this one, so it's 60. So we're referencing the 30, 60, 90 like so, like this. Our perspective is always on the origin from the... I guess that sounds weird. Perspective. Well, the perspective is always held on the angle that's contacting the origin. So this one right here. Alright, what about this 30, 60, 90? We know this is going to be root 3, but it's negative. This is positive x direction, so this is positive 1. Hypotenuse almost always positive. We have enough information. Sine is going to be opposite over hypotenuse. Done with that. So, not too bad, right? We'll see. Cosine. Cosine of 150. What does that equal to? It's 90. So we're going to be in quadrant 2. Right here. Our triangle is here-ish. What kind of triangle is that? It has a negative x coordinate, positive y coordinate. What exactly are we referencing? This is going to be 150, which is 30 degrees short of 180. So our triangle we're referencing is a 30, 60, 90. Focusing on the 30, where the ratio's positive 1, negative root 3, positive 2. Cosine is adjacent over hypotenuse. Finish with the problem. We're at a tangent of 315. Where are we? Well, this is close to 360. It's past 270, so we're right here. So from here, 90, 180, 270, 315-ish. We're right here. Always connect the stick directly to the x-axis. Make note of the signages. This is going to be positive direction, negative direction. What triangle is this? Well, how short is it, right? So I'm going to do the 360 minus 115 instead to get 45. So we're 45 short of this one of reaching full circle 360. So we know this one here is 45. So all we're doing is referencing a 45, 45, 90. The ratios are 1 to root 2 to negative 1. It's tangent from this angle that's contacting the origin. It's going to be opposite negative 1 over adjacent 1. Final answer. And we're good to go. What's the cosine of you're going to start getting used to these numbers as well. Like after you get used to 30s, seeing 30s and 60s and 45s, you're going to get used to seeing these ones. Okay, what is that? This is past 180, but it's less than 270, so we're right here-ish. So how far past 180 is it? Let's just subtract 180. So it's 45 past half circle. So this is half circle, this is 45 past. So we're here-ish. What are we dealing with? Negative, negative, 45 past. So we're dealing with a 45, 45, 90. This looks like a funny frog face. So what are the ratios of a 45, 45, 90? In conjunction with these signs, it's going to be negative 1 to negative 1 to root 2. It's cosine, adjacent, over hypotenuse. Rationalize if you have to. Final answer. Okay, I think that's going to cover it for today. I felt like it was like a lot of information, a lot of mechanics. I guess the first half was just review from last time, so that's not new information. I guess just like a little bit of new information, like trig functions only give you proportions, they don't give you actual lengths necessarily. And then we're also, for the second part, major part of this stream, we're just focused on the angles that are greater than the ones that are 30, 60, 90s, and the 45s. Okay, and that's basically what I wanted to cover, I guess because I'm tired. Next up, we're going to be reviewing these concepts again. Now, the problems I'll be writing will be incorporating stuff like this. And then we're also going to be covering negative angles and angles greater than 360 degrees. So, that's the plan anyway. That's it for today. You have yourself a good one, and I'll see you in the next time.